So this chapter, guys, talk about electrical service. Electrical service 99.99 always start with a transformer. Always start with a transformer. What you're looking at, guys, it's called substation. What you're looking at is unit, what they call it, unit substation. And we did these in hospitals, sport arenas, and so forth. What would you do with this, guys, is you bring, as you can see, you bring your high voltage cables in, and then you get your low voltage cables out. In this case, you will be getting your low voltage cables out of all these, and you go inside your building. Okay? So, where would you use something like this? Notoriously famous, guys, in hospitals, where you have a substation like this. With a high voltage, we have a hospital, I believe in Mayo Clinic, they took 13.8 feeder from the basement all the way to the 13th floor, and they fed everything down with that 13.8. So, let me just tell you about the high voltage. That high voltage section could be 13,800 kilovolt. The transformer could be as high as, say, let's just say 1500 kVA. And this secondary side, let's just see what a size that could be 1500. Divide this by 480, divide by 1.73. 18, that could be 2000 amp. And the voltage on this baby is actually 480/120 volt. Does that make sense? So you have a high voltage section, disconnects and fuses, and that's going to a transformer that transforms it from a high voltage 13,800 volt into a 208, a 120, or 480/277. This should be 480/277 to 480/277. This probably happen in bigger buildings where utility bring you a feeder high voltage, and the utility will have control over the high voltage section, and you have control over the low voltage section. Sometimes they have the transformer, and the high voltage section is part of the utility. Not commonly used, as I said, except in major projects. Sometimes, Phil, as I said, in hospitals, you as an owner have a full control over this, the whole unit substation, so-called unit substation. You have full control over the unit substation. Let me tell you what we have done in a unit substation that you have full control over it. You bring, so this is kind of utility work. If it's not utility work, what we've done is you bring a 480 system, 480/277 in to a transformer, let's just say 1000 kVA into a 208/120 volt system, all three phase, obviously, all three phase. I want you guys to look at a substation like this has three compartments. One compartment for the whole low voltage, the distribution section, one compartment for the transformer, and one compartment for the high voltage. So tau, it could be either the top coming for utility type, the bottom coming for us. So you take a 480 feeder into certain area, and you put your transformer as well as your distribution panels and the feeder all in one big panel. You bust them together. Who cares? It's a nicer, this design is much cleaner, nicer, coming in hospitals, sport arenas, and so forth. What's the alternative? The question is B, what's the alternative? What's the disadvantage of this? It's bendy. Your transformer is going to be a dry patch transformer sitting indoor, and they're all bust in. Can you guys see how they're all bust in? They're not cabled inside the enclosure. You're going to hear about this one for hospitals and sport arenas. Any comment about substation? Unit substation. Every time you hear them talking about unit substation, they talk about three things: a high voltage section, which is we talk high voltage transformer, and low voltage. Now, the high voltage could be as high as 13.8 or as low as 480. The transformer could be, could be 2,000, 1,500, all the way to 500 kVA, any size. The secondary side most likely can be 480, 277 most likely, or 208, 120 if you're bringing 480, 277. Any question guys about unit substation? What's make a unit substation? A transformer, a primary high voltage section, and a secondary distribution section. Any question about unit substation? Can I have thumbs up, Chad? We know what a unit substation is. Hospital, notoriously famous of that. Okay, so that's basically very expensive, again, very expensive design to do a substation like this. I want to remind you guys, this is the table 250. We use 250 to size overcomputation device for transformers. I'm not going to go over this one. This is one, William, my friend, this is one of the best tables, the best illustration that describe this table, which is, you guys, I'm sure you're familiar with it, from Andy C code book that we went over a couple of times and we will continue to go over in 1 second here. Table 450.3 A and B. While it's powering here. So while it's powering, guys, I wanna bring to your attention, when we have a transformer that we have control over, we need to size the primary overcomputation device for the transformer. Do you remember how we did that? We will be doing it next quarter too. The secondary overcomputation device, the secondary feeder, and the primary feeder, as well as the transformer. They size them based a bunch of things from the table. If the impedance is less than 600, overcomputation device, if it's fused 300, if it's circuit breaker 600, and the same thing for 300, 400, secondary overcomputation device 600 over 600. Here's how we do it. If it's under 600, this is how they do it: 120 times the full load current of the transformer. Then you go to primary over 600, secondary over or under 600, and in different locations. So this, as I said, this table, I will go over more of this table as we go to the industrial. I'm just going to flash it. I know when we used it, guys, we used it under these circumstances, which is right here. Transformers. And when you see it, probably you recognize it. This one. You guys remember that? 450.3A. 450.3A. We said it starts with transformers. If a primary or the secondary is over 600 volt, so we start with the primary, secondary over or under 600 volt, and you do the whole calculation. And if you guys, I don't know if you remember, I told you, if you don't know anything, any location, you default to any location. This impedance, you default most of the time for fuses on the primary. That's your default. On the secondary side, if it's 600 volt or less, most likely it's going to be circuit breakers, but it doesn't matter in this case. So that's your default unless you know otherwise. Unless you know otherwise. Unless you know otherwise. Any comments, any questions? So what the author of this book did is took this table and put it in a nicer format. Really. I want to bring to your attention, Bill, my friend, every time you see that asterisk here, where did it go? Note. Here, there's a note number 1. Do you guys remember what note number 1 says? If you don't hit the standard, what do? Go up. If you can't go up, what are you going to do? You have to go down. So if you don't have note number 1, then if you don't hit the standard, you have to go down. And we all know where to find the standard. 240.6. 240.6. We will be using this table, guys, for a lot of calculation. Any question about this table? So what the author did, they grabbed this table, and this is for if the voltage, the primary or secondary over 600 volt. If both the primary and the secondary are less than 600 volt, then you use this table, and you're going to default primary, secondary protection. Just default to this one. Most likely current over 900 and current less than current of 900 amp or more. So this is your default. Most likely secondary protection. Well, if you have, this is also a couple of applications that we use, primary and secondary protection. 250, we're going to use this example, and 120, these two. I want you guys to look at this one because we have an example right now that using this 250 and 120 for a transformer that's both the secondary and the primary are less than 600 volt. You don't have to memorize that. All what you need to do There's nowhere to find it. This applies for everything if it's 600 volt or less. The one before it, if one of them, primary or secondary, is more than 600 volt, you go to A. B, if both of them are less than 600 volt. I don't want to go through the details, guys, on multiplication because it will be coming in the industrial. Any comments about this? Comments? I'll show you a calculation based on the bottom one that we did. Okay, so they took these, and the author puts them in a really nice format right here. Primary overcome protection device. So all this what you see is really summarizing these two tables. Summarizing these two tables. Again, we will be using them, guys, as we move more into the commercial too, in the industrial lab. Okay, so that's this one where I want you to pay attention. This is very common, and we're going to be doing a lot of calculation based on this one, guys. This is if you have a system, you have a system 480. Your system is 480 277 volt, and you need to convert it into 208/120 volt. And everybody knows why would we do something like this? Because you need receptacles. How would you get receptacles if your system primary is 480 277? So what you do, you have a panel or this huge disconnect next to the transformer, and you have a secondary protection, as you can see right here, secondary protection for the transformer, and you size the transformer. They're giving you an example, and I promise you we're going to do a lot of examples like this, guys. But before we go anywhere, I'm going to show you the transformer that they're using. As I don't know if you see right here, it's 500K, 50 kVA. The primary is 480, like we said here, and the secondary is 28120. So the primary is actually a delta. Well, coming from well, it's not a delta, but it's 480 ohm. We don't need a neutral on the primary. Any question, guys, about the primary 480? Fuse disconnect coming to the transformer, going to the 28120 to feed the receptacles. Feed receptacles. Okay, who cares? Again, we will be doing a lot of calculation like this. The first thing to size, we need to size these cables, guys, here, and we need to size these cables, and we need to size the fuses, and we need to size the circuit breaker on this side, right? That's what they hire us to do. To size the primary, can you guys see how the example, to size the primary, find the full load current on the primary side, piece of cake. Take the kVA divided by the voltage and 1.73, get you 60. To size the, so that's the primary. So what they did for the fuse, guys, there are two sizes, maximum and suggested. Maximum, if you look at, since we have primary and we have a primary and secondary protection, we can go as high as 2.5. Can you guys see 2.5 times 60 equal 150? Is 150 a standard fuse? Yep, based on 250. So my primary fuse is going to be 150. So my primary fuse right here is going to be 150. It could be lower than that. It could be lower than that. But my primary fuse is 150. Any question, guys, about primary fuse? 2.5 times 60. Based on the table. Equal 150 even. So the fuse is 150. Okay, the secondary fuse, if you look at what they did for the secondary, guys, the secondary, the same thing, they found 139 amps on the secondary, multiply it by 1.25 from this table, 450.3b, and that will end up 173, and because there is a note number 1, you can go to 175. So this baby here is 175, 175, 175. Any question, guys, about sizing the primary and the secondary? We will be doing these in commercial and in the industrial a lot, guys, because we don't have a transformer right now. We will be doing a lot of examples about this, I guarantee you. Okay. Any question? Any question about this? The one thing I want to bring to your attention is then the way we size the conductor here. See these conductors? Can you guys see the conductors? Match, I always say match overcurrent protection device on that panel because it's ahead of a panel. Match the overcurrent protection device. On this one here, I usually size it based on 125. So the size of my cables will be 75 amp cable. Will be 75 amp cable. I don't know what they're using here. 75 amp cable. Any questions about this? Questions? Again, we will be doing calculation in commercial a lot. I want to bring to your attention a few things. Number one is this one, grounding electrode conductor, right at the service, separated drive system. Number two is supply side bonding jumper, this guy. And number three is equipment grounding conductor. Can you guys see these, the grounding stuff? Equipment grounding conductor. Everybody knows how to size the equipment grounding conductor. How do we size the equipment grounding conductor? Based on the overcurrent protection device ahead of it. Based on the overcurrent protection device ahead of it. So the overcurrent protection device is 150 right here. I can size the equipment grounding conductor. Grounding electrode conductor, this one is called system bonding jumper. And I'm writing the names right now because when we move into the industrial, I guarantee you, you guys will be doing a lot of calculation based on these. For the time being, Jackson, my friend, I want you to understand that that green conductor coming from the panel to the transformer is called equipment grounding conductor. That conductor that's going to the ground is called a grounding electrode conductor. Tying the neutral to the ground is called system bonding jumper. System bonding jumper. The grounding conductor from this panel to this panel, they call it supply side bonding jumper. Supply side bonding jumper. Supply side bonding jumper. And you can see in this, it will tell you where to go to size these guys. For the most part, we size them. We actually size them based on the conductor right here. So we size this one and this one and this one. All of these, supply side bonding jumper, supply bonding jumper, or system bonding jumper, main or grounding electrode conductor based on the conductor that's coming to the panel. Again, I promise you we will be doing a lot of calculation on this one. For the time being, if you do me one single favor and just understand how the system is put together, and all what I need is just understand the names and how it's put together. Cool? This is one of the most important pictures you're going to have about, this is called separately derived system. I don't know if you guys can see how we created our own neutral. Can you see the neutral created right here? And we pulled it all the way to the second panel to have our 28120. Any comments? Allah Ripo, my friend. I feel it's Friday today. Quieter than normal. Chris used to ask a couple of questions now. We have to send him a YouTube channel video. Okay, the second ones, guys, I'm not going to emphasize too much. I know we've done them in our lab. Utilities tend to have single three-phase transformers. They call them banked together to make a three-phase system. Not commonly used to wire a building or by electrical engineers like us. So this is a couple of wiring diagram where you can bank a three-phase transformer, three single-phase transformers. So I can bank, this is 75k VA, and another 75, and another 75. Bank them together to get me 75 times 3 kVA and feed a three-phase system. Any question, guys, about banking transformers? Banking transformers. I don't test you guys on the connections. You're not electricians. We not commonly use. We rarely use this one in the construction. Mostly utilities. It's good to know though. There's a few things where you can look at the primary. Your primary can be 4160. Here, your secondary in this case 480 could be 208. It could be 600 volt. For the most part, this is your primary Y delta. This could be 13.8 K, 12.47K. That's what commonly I want to emphasize. At least that's my experience with them. Is we use them with high voltage on the primary. The primary usually high voltage. I've never seen them where the primary is less than 600 volt. Usually it's higher than 600 volt. Utility type work. Why would they do something? Why would anybody do something like this? Have 3 barrels and tie them together to make a 3-phase system. The advantage of this one, I'm sure you guys, when you did it with Gary, and I know we did that one, right? You've seen these pictures before, right? Right, Phil? In the first year, you know? So the advantage of this system, I don't like to emphasize it because we don't have control over it for the most part. The advantage is if one of these transformers is to crab on you, burn, right? You can hook it open delta, but that's utility work though. You hook it as open delta, you can rehook this one and your system is still up and running at derated value. At a derated value. So that's an advantage. So you rehook it, go bring another transformer, put it back, and you're up and running. So, and your loss is less. Imagine if one of these, if this is a 3-phase transformer and one coil burn, the whole transformer is gone. But this one, if it's 3 single-phase transformer, one coil burn, that's just one big barrel. Get it out with no one. Anyway, so that's what I wanted to, the only thing I wanted to emphasize. This is what 28120. The first one is okay, 28. This one, just FYI, guys. This is how your house and mine is wired in the US anyway. This is most likely what we have. 2 hots, probably 13.8K here. And that's where you get your 240/120 volt single phase system. 90, I would say probably 90% of the dwellings is wired this way. Who controls this big fat boy? Utilities. Utility, electrical utility. How does it look like? The H for the high, X for the low voltage, and I want to spare you the connection. Okay, so I just thought to mention that one. You can have an open delta. I don't know if you see here. Here you can see how I lost one transformer, burned, got eaten. I continue to run at 4160 here, 4160 volt, and rewire. Look how we rehooked him up to continue to get me the 240/120, which is center tab delta, center tab open delta. Open delta center tab. Can you guys see the tab here, guys? Where the tab, that tab? It's called center tab open delta. I don't like to emphasize it, especially in the second year, because of one reason. We don't use it in a commercial industrial building. Commercial buildings. Sometimes in industrial we do. Just be aware of it. Tie them all together to make a 3-phase system. You can make a primary 3-wire delta Y, 4-wire delta, center tabbed, a couple of connections. Okay, this is where I want you to wake up if you guys, if I put you to sleep. Cable connection between transformers. Most of the time, when you bring to the building, you can bring the power to the building from a transformer owned and operated by the utility. So one way of bringing it in a commercial probably building is you bring current transformer switches. You can bring your feeder right in here into a current legacy current transformer, meter the equipment, and then feed into your switch gear. So you would transform, if you're downtown Minneapolis, right here, that's probably what you're getting the power as. You bring a busway like this or cables from underground vaults that are full of transformers, network transformers, and they pull them directly into your current transformer, so you can CTs and PTs them. This is how you can meter it to your main disconnect, right? And then you feed it down into your 4,000 amp switch gear. That's it. We call this one service entrance conductors. Service entrance conductors. Service entrance conductors. And so you can come overhead or underground in this system. In this particular system. This is another common way, guys. All what we're talking about the service. How do you bring a service to the building? How do you bring a service to the building? Okay, so This one, if you guys look at it, primary conductors in conduits from the pole into the bottom of the unit substation. I have a unit substation coming in industrial, mostly in industrial, and I have this one is for 4160 volt, 460 volt, 4160, right? And just put voltages here, 4160 volt or 13.8 K. And I don't know if you guys can see, you brought the power in here into your unit substation. The high voltage, can you guys see the high voltage switch gear with a fuse, current transformer, you meter it. You have also transformer section. Can you guys see the transformer section right here? The high voltage section right here. Then from that transformer, you went into the low voltage section and into your 4000 amp switch gear. Phil and Jackson, my friend, the utilities, they call this primary feeder. They call it the primary service. You're going to hear them in the industry, William, talking about two types of services, the primary service and secondary service. Most of what you're going to be getting is secondary service, which secondary conductors, 480, 277, 28, 120. Very large customers like the U of M, 3M, Mayo Clinic, all these big corporations, they get the power at a high voltage level at 13.8. So up to this point, guys, I don't know if you can see, up to this point here, all this is high voltage. High voltage. What high voltage? 4160. When you come over here, it becomes 480/277 because you went to a transformer inside XFR, transformer to transformer. So this in reality, it looks something like this when you draw a riser for it. You fuse it, then you come to a transformer. Out of the transformer, you go, in this case, fuse it, you put the fuse over here, and then you go to your panels. And these are also circuit breakers. Does it make sense? That's what the riser looks for, the substation. And in a case like this, you're going to have a 13.8.8K. This will be a 480/277. And this will be this is one section, two sections, three sections. You can do it this way in three sections, or you can build them all together in one big box. They call it unit substation. Tom, my friend, probably 5%, 10% of you will deal with this. 10%, you're going to deal with this with 10% of the time with primary service. Any questions about primary service? Beautiful service. Where do they meter you? Can you guys see where they meter you? Where you're going to pay? They want you to pay, so their metering is happening right here. They call it hot metering. They meter right at the substation. They put their meter CTs and PTs and put it right at the substation. Any question about this substation, underground feeder? Phil, depending on where you put your service point, they call it service point, the contractor this could be service entrance conductor, means it's owned and operated by you, or it could be underground service lateral. Service lateral, meaning it's owned and operated by the utility. Very, very important term. So if this is my service point right here, not commonly used, then this will be service entrance conductor. Who cares? As a contractor, you have to dig the trench, put the conduit, and pull that medium voltage cable. Not a big deal. If you put, most likely it's going to be the service point, they call it service point, right in here as you enter the switch gear. That's it. So then who's going to be bringing that conduit and the cable? It's going to be most likely the utilities. Or the utility might ask you to put the conduits for them because you're going to interface. Just put the conduits up to the pole. They'll take it from this point up, the conduit. And then they come and they pull their conductors in IC conduit. Can I just get you to understand? We'll talk about service point in a second here. Service point. This is the point where your responsibility start and the electrical utility responsibility stops, and vice versa. And you can see the articles in the NEC code book. This is more like a Jackson, this is more what we do. Really, this is very common. That's, I would say, 80% of what you're going to do in a commercial is going to look something very similar to this. Look what they do. You can have you have the high voltage coming from this. Let's use high voltage. You bring high voltage coming from here underground to the high voltage section of the transformer. This is primary service conductor. Primary service conductor coming in here, and from the transformer, you take it all the way to your parallel to your main disconnect to the building. And and then you have CT cabinet. You guys remember the CT cabinet what we talked about when we were doing Revit? We said you have to have a box with CTs that take 1000 amp and turn it down into 5 amps so the meter can read it. Otherwise, you're going to burn the meter if you put 1000 amp into it. You can see with CT cabinets, you're going to have your CT cabinet here with a transformer CT cabinet, and you come in. I would say most likely you are at 90% of the time, commercially, that's what you're looking at. 90% of the time, that's what you're looking at. Any comments? And that's what you guys did with me, right? You put your CT cabinet outside, you brought the cable from the utility transformer to the CT cabinet into the building. Okay, who owns what? Who owns what? Very important when you become a contractor, Phil, who's going to be doing what? In a case like this, most likely that right in here, inside the transformer, this point right here is called service point. Service point, meaning anything from this side in is my responsibility, right? My responsibility. Anything moving forward this way, whose responsibility is this would be our report, the electrical utility. Any question about this, guys? You guys have the same pictures. Keep these. These are typical of what we do in, as I said, 90% of commercial buildings. You bring a feeder from overhead, from underground to a transformer, like you see. Now this conduit and that cable most likely will be installed by the utility. They might ask you to put the conduit for them, but they will pull their cables up to their transformer that they will install. Their transformer, they install their transformer, they have to install it. So, and then you put your CT cabinet next to them, and you go to your building. Any questions about this? I talk about seals here. We're not electricians, but as a project manager, every time you enter, you have to seal. Seal, they fill it with a caulking or some type of a seal where critters and creatures can't sneak from this into the building and eat the cables and get electrocuted. So so they have this type of a caulk that you can fill it. It's explain it to me. Anybody, you've seen the seal? How do you explain it? It's like yeah, the seal. Like similar like caulking when you caulk a hole or something. So you because you put your conductor here, there's still room here for critters and even for environmental air to come. You need to completely isolate it. Any question, guys, about this? Okay, so that could be your service the bottom here. That could be your service entrance conductors or service lateral, depending upon where you put your service point. And we're going to talk about service point is very important. The first thing when you become a project manager, guys, you have to ask is about the service point. Look at this underground. The same thing. This is most likely in downtown Minneapolis and all this stuff. They come with the high voltage to a transformer in a volt, and from the transformer they go to the building. Transformer, can you guys see where the meter is sitting right here inside the building with the main disconnect? So service conductors run into the building. Sometimes they put the service point right here. If the service point right here, who owns everything from here on? The utility. You have to decide where the service point is. Every utility has it slightly different. I'll show you in a second here. Really nice pictures about service point. Okay, meters. Most likely, guys, if you go higher than 400 amp metering, you're going to get into CT cabinets. There are a couple of pictures of nice looking meters. This one happened to be 208-120. This is my 208-120, three-phase, 200 to 800. I think they can get them 800 at this voltage. 13 terminals. Look at all these terminals that you have here. 7 terminals get you up to 200 amps, and then you have 4 120. This is the most common one for residential. That's what you see in your residential. Here you're using some type of CTs and PTs in these areas. Here you're directly measuring the equipment. So different time. Most of the time, guys, is we in a commercial building we have a CT that convert. You know, you put a CT here, and you bring a feeder inside it. You put the feeder inside it. So this carrying 5,000 amp. I'm exaggerating here. This will be seen as 5 amps. So like a current transformers, it transforms the current from one very high level into one very low level, so you can measure it. Couple of metering option. Okay, here's what I want you to wake up, guys. This is really I think one of the most important things that you have to understand when it comes to interface with utilities. Service point. Can you guys see where service point is? Look at the word service point. That's decided by the utilities. So look at this. I'm coming with, this is utility. Can you guys see? This is owned and operated by the utility. If I put my service point in this area, see where my service point right now, I'm going to emphasize my service point is right here or right here, okay? Then this area is still operated and owned by utilities, called service drop overhead or service lateral underground. And F is the one that I own and operate in this case. If I put my service point right here, this area here is my jurisdiction, the premises. This area is my jurisdiction. Most likely include the overcome protection device too. Include the overcome protection device. So most likely, so they bring the feeder. If the service point is at the meter, then it also includes the feeder from the meter right here. That's probably 90% of the time, guys. You're going to come to the meter cabinet, from the meter cabinet into your building. That's called service point. If you put your service point right here, can you guys see where you put your service point right in here, right? Then everything here is owned and operated by you. Owned and operated by you.
Is there a rule of thumb guiding the position where you put your service point?
Yes. This is commonly, if you're going, most of the time, your service point in a commercial building, it's going most of the time, again. Here's my, let me just draw, here's my transformer. Here's my CT cabinet, transformer, and here's my building, right? So most of the time you come to the transformer in here, and then out of the transformer, you come with the CT cabinet up to here. I will right here to the CT cabinet. Everything is red as operated by the utility. Out of the utility, let me say green. Out of this CT comes to inside your building. So my service point most of the time will be right in the CT. Service point. Most of the time, your service point will be right the CT, where the meter is, by the way. They put your meter right in here, too, which is where the meter is. That's the most common application where your CT is. So anything, let me tell you what you own. What the utility you own and operate is anything that's red. Anything that's red, the utility own and operate. They own the transformer and the feeder to it. They own and operate the cable to the CT cabinet. They might ask you to bring your put a conduit for them. You own and operate everything else. The CT cabinet, you own and operate it, well, you own it, and you bring your cable to the building. That will be very similar to the first one right here, where the CT cabinet is. This most likely will be the CT cabinet or a meter. This one is mostly, if you put the service right here, guys, mostly like residential. You bring the overhead to a certain point. Actually, it's not right at the transformer, to a certain point, and you tab into it with the service entrance conductors. I don't know if you guys can see where it says, this is a feeder, this is service entrance conductor. I don't know if I make it, let me take a picture, a snapshot of that, and get rid of it. Okay, based on where you decided, it becomes, can you guys see the F? This becomes, right here is a feeder, and right here is a feeder. Service conductors, let's just, you blue. See, this is a service conductor, so you own and operate it. This is a service conductor here. You own and operate it. You service conductors. And of course, these ones here are branch circuits, the branch circuits. Any comments, any question about the service point? What's the service point? The point where your responsibility stops or starts, or the electrical utility responsibility stops or starts. Here's the project that we have, guys. This is a poor man's job design. When you bring, well, actually economical design for a multi-occupancy building. You bring a feeder and you tab it. You tab these feeders to feed multi-occupancy building, right? You tab it, literally, physically tab it. So that's the building that we have. Have 1, 2, 3, 4, 5, 6 feeders coming out of that feed. Now you can do it this way. You can do it this way, right? Or in a case like this, can you guys see each one of them has its own meter because they're different tenant? You do this one in a strip mall. You have a strip mall, and the strip mall guys have different tenants, right? And when you feed every tenant, what the easiest way to do it is to bring the feeder to a gutter like this, outdoor, and literally take the feeder, tab into it, and go to every area. And of course, you have to land in the meter. Out of the meter, you're going to go to the first disconnect and the second, and so forth. Any comments about this? This is the cheapest, probably, way of doing a strip mall with multi-occupant, different. Yes, sir.
So is that CT cabinet service all 6 disconnects, or just
No, each one of them has its own meter.
in the CT cabinet right
EMT connect to current transformer. No, it's only servicing the bakery because it has a lot of. Very good point. The question would be, Chad, why? I know here's a meter here. Got it. These are meters. But why did that big fat thing set here? Because the load on this building, I think the riser is coming in a second here. The load is very high. So if your load is higher than 400 amp, you need CT cabinet. That's why they have a CT cabinet here and they don't have it anywhere else. Bakery. It's a 400 amp. Everything else is 200 amp or less, except the bakery is 400 amp. So we need a 400 amp here, CT cabinet. Any comments, guys? Any questions? So these are what I wanted to show you. Here's how they wire them. Alanipo, this is the bakery, exactly what they wire. Can you guys see how they came out of here into my CT cabinets? I don't know if you can see them. These 1, 2, 3, and then these, they're wired. They wire them and they bring them into the meter. They're wired to the meter. So they sense, and they are most likely these ones 400 amp to 5 amp. They call them 400 to 5. So every time it sees a 400 amp coming into the building, it will be seen as 5. Now you do proportional. If it sees 100 amp, it will see less. You do the proportion for the amps. Can you guys see how they tab them with these logs? They land them in here and tab them directly with the logs. And then we have our grounding electrode conductor in the cabinet, and we have to tie the grounding electrode conductor. You're going to be bonding the grounding electrode conductor to the, well, it's in this case, it's bonded to the enclosure, to the gutter. Any comments, any questions?
Yeah, what does the city cabinet now do for the bakery?
Why it's due for the bakery, not for, because the bakery is the largest load here. It's a 400 amp. This one, this.
Protective device for the
Oh, what is it? Let me give me 1 second here. Let me just see what's the other one. What was that one? This is Yuri. This is a 200 amp. This one is 200 amp. Okay. Already for up to 200 amp, the electronics can take the amps and sense them directly, the meter. If you go higher than 200 amp, if you put more than 200 amp through the jars of a meter, you'll burn it. So the smarter than Chad said, okay, I'm going to put a CT. So here's my CT, and here's my, it's basically current transformer, and here's the current. So if there's a 400 amp in 400 amp in phase A, this is phase A, this CT cabinet will be seen as 5 amps by design. Okay? Now, suppose I have only, this is 400, suppose I'm pulling only 200 amps here. So then you're going to hit 400 goes with 5, so if you can do proportional, 400 amp to 5. If you have 200 amp, what do you get? Right? 2.5 amp. So if you have a 200 amp going through the system because you're not loading the system, then you get 2.5. So what it does, it takes a very high amp, reduce it to acceptable measurable value. Otherwise, you're going to burn the equipment, or your coils inside the meter has to be so huge.
So simply it's a kind of protective device.
It's really, it's not a protected device. It's a converting device. It converts very high amp to very low amp, so you can sense it safely and economically. So here's the one-line diagram, guys, for this system. Do you see where CD cabinet is needed? Can you guys see where it says 400 amp disconnect and 300 amp fuse? That's why, right here. That's why we have a CT cabinet here. And a lot of people, can you see where they describe the CT cabinet? Can you guys see that little symbol with meter? That's a CT cabinet, or the CTs. Everything else will be measured directly. So that's a riser for the project that we have sized, and we went over some of this. This is bonding and grounding for single phase. We've done it in residential. Bonding and grounding, guys. The only thing I want to say at this time about bonding and grounding is you have to create a grounding electrode conductor at the service. You have to bond the neutral to the grounding electrode conductor, right? The neutral. And the calculation is coming. So here's my neutral. I'm going to bond. Can you guys see that neutral is bonded to the grounding bar, and the grounding bar is bonded to the water. It's bonding to the concrete. So a lot of people, the codes say you have to have one grounding electrode system, but if you have more than one, you have to bond them all together. Does that make sense? So I can get away with one grounding electrode right here, which we will talk about this one, guys, how to size them and all this good stuff. And then the service conduit, Phil, the service conduit, if it's metallic, they're bringing your service, you also have to bond it. And you can see how they bond the service. They call it equipment bonding jumper supply side, bonding jumper. You have to have a bonding bushing and bond the service conduit. You have to jump around the meter, so if they take the meter, you don't interrupt the continuity of the grounding electrode system. Again, we will come back to these guys and connect them. Equipment bonding jumper, every time you have to bond across equipment if they are not continuous. I want you to look at this one, guys, and for the time being, please identify the following. This is my service. This is called main bonding jumper. Can you guys see that? That's the only thing I want to at this time. This is grounding electrode conductor, main bonding jumper, main bonding jumper. And this one also grounding electrode conductor. This one is system bonding jumper, and that's and this is supply side bonding jumper. I'm not going to go over calculating them. You will hear me talking a lot next year, next quarter, about how to size the system bonding jumper, supply side bonding jumper, and so forth. For the time being, know how to identify them. I know we touched on them, but we'll go into the details of calculating them later on. Okay, GFCI protection and so forth and bonding. The reason why we bond equipment, guys, because we don't want things to sit at different voltages. For example, take this. If this has to be bonded through the grid. Why? Because it has electrical wires in it. If it gets hot and Chad grabs into it, and because he's always moving around, grab it here and grab the wall. Now you got yourself a 100-watt bulb burning. So what they do, they ground everything that could be energized, not just a conduit. Anything that carry electrical or next to the electrical equipment have to be bonded together. Why? Because you don't want one level of voltage here and one level of voltage here and Chad grabbing on this and that, and you have a current going right through you. So we'll talk about the main bonding jumper at the service too as we go through. Again, I promise you we will talk about main. This is a bonding jumper at the service. We'll go through that. The same thing, bonding jumper at the service and equipment grounding conductor and so forth. The equipment grounding conductor or equipment grounding conductor, guys. If you have a conduit like this one with a flex at the end, right? You have to pull an equipment grounding conductor because the flex is not rated as an equipment grounding conductor. So you have to pull the flex on that one. This is just to tell you why do we ground things, because you don't want to arc and spark and so forth. GFCI protection, we talked about GFCI, guys, looks at the current in, the current out. Okay, I'm sorry, these are the CTs. These are your CTs, different type of measuring CTs. Different type of measurement for CTs. This one versus that one. If you have a ground fault protection, guys, what they do in higher voltages, they have to put a ground fault protection for equipment 1,000 amp or higher. Excuse me. So that's a means of providing a ground fault protection for equipment. Ground fault protection for equipment. I want to just say one little thing about this one because we're coming to it. This required for any system 480/277 volt and 1,000 amp or higher. If you have a system 1,000 amp or higher, you have to provide something called ground fault protection. We will do that one in the industrial because that's what we have. We have a 4,000 amp switchgear. What this is looking at, guys, it's looking at the ground fault. There could be, under certain circumstances, there could be a current. If you have a ground fault right here, the current here coming on the ground could be high enough to create a fire in the building without the circuit breaker being able to interrupt it. So the smarter than Chad decided to put a ground fault protection on equipment like these. CT cabinet. Sum of conductor equals 0. Okay. So I don't know if you guys can see how it looks like. If the system is up and running, look, A, B, C, D, the neutral, all of them are going to be summed to 0, right? Nothing is happening. The minute that you have a ground fault, some of the current will be going back to the ground, right? Then, excuse me, then it will sense that there is a difference in the current, unbalanced, not balanced here. And you could trip, you could alarm. You don't have to trip. You could send a signal to your cell phone saying you have a ground fault. You could do anything you want with the ground fault. Couple of CTs, I believe. And okay, bonding, couple of bonding hardware that they have, guys, here. Calculation, load calculation. We did a load calculation, so I'm not going to bear you with these. This is the table that we size the grounding and the third conductor, main bonding jumper and system bonding jumper. A couple of things about the panels that you guys have to know. If you have a panel, your panel has to be labeled with the available. If it's a service short circuit current, if it's a delta, it has to be labeled with delta. It has to have a directory that says all the identify the location of all the circuit breakers. And I'm going to stop right here. Any comments, any questions? I promise you one thing. All this, especially this article, guys, we're not done with it. This will come and hunt us in the industrial, because that's exactly most of it is industrial, especially with the transformer and substation. We're going to get into more deep into the grounding and bonding, all the grounding and bonding. We have examples how to size them, and into the transformers too. Size transformers, primary, secondary, and so forth. If you read this chapter good and understand 70% of it, you're right there, very close to where we're going to be next week, next quarter. Shall we have a quick break?
Please, will you please explain the main difference between the main bonding jumper and the system jumper?
Okay, let's go back. Main bonding jumper system. Well, I can explain it in 2 words. The main is at the service. The system is at the transformer that you own and operate down in your building. Okay, there's an example here. Let me just see. That's really, they do the same thing. They actually look alike, and we size them alike. We size them exactly the same thing. Let me see if I can find it. Of course, you don't want to, when you want something. Okay, there was one. Okay, here you go, right here. Well, this one. Alaripo, this one here. This is called the system bonding jumper. System bonding jumper. Why system? Because I own and operate all of the following. This is all in-house. System bonding jumper. Make sense? We have the transformer. We took the 480 inside our building, volt, and we converted to 208 system, and we created a new neutral. They call it system bonding jumper, right? Almost always, when you take a 480 to a 208, you have a system bonding jumper. Now, the second one is right at the service. I think we have a few of these at the service. There was one when we have diagram. Okay, here's this is not as clear. Right here, a lot of people see that. Okay, so this is grounding conductor. This is service disconnect, main bonding jumper, right in here. Can you guys see that? Now this is, I want to remind you, this is service disconnect. This power is coming from electric utility, not from a feeder. That's my service panel. Right inside the service panel, that cable here is called main bonding jumper. They are the same. They do the same job. They just call them different. We size them the same. They just call differently. Cool? And I promise you we'll hear more of that. I want you guys, I want to go over one more chapter, please. Can you guys go outside and debrief a little bit? And then we'll come back.